Hello everyone, so we are back with more regression. Basically what we are doing here is similar to what we've done with the regression in the basics of sklearn, but this has a little bit of a twist. We'll see why we would need more features to do a proper regression. So let's start again. We'll do some imports here. I believe you are all now familiar with these imports. Most important thing is to have the seed fixed at the start of the file, so make sure that the random number generator will produce the same results every time. This is mainly for testing. In actual deployment you would actually remove this line. So let's run the first cell. Now we're importing everything and we are making a dataset, and basically what we're doing here, we're saying we want 1000 samples. Each one has 3 features. Out of these 3 features we have 2 informative. Means that 2 features can actually have good relationship with the output. This will return us to will give us x and y. X are the number of samples on the row side, and on the columns we'll have 3 different features. We'll pack this into a data frame and we'll set y to the a new column in the data frame, and we are ready to do the plot, the pair plot, so we can see what we have in terms of a data set. And there we go. This is our data set now. When we glance over it, we can see that x0, 1, and 2 don't really have anything in common. You cannot deduce x1 from x0 or vice versa. Same goes for x2 and so on. But we do see a relationship between x1, the x1 feature, and the y vector, the target value that we are trying to predict. We can also see a maybe slightly vaguer relationship between x2 and the y. And yeah, so right now we have 2 candidate features. We can select one of them and do a regression model, and then we'll see how this performs. Similar to what we've done before, we will import the linear regression model and the R2 score to evaluate the goodness of fit. We will slice x and take feature number 1, not 0. This would be x1, and we'll take the entirety of y, which is only one dimensional vector anyway, make a linear regression model, do the fit, put x and y here. You will get the y hat when you predict, and then we derive the mean square error and our squared score. All pretty much standard stuff. We'll print that and then we will plot the figure. So when we run this one, we get a fairly high mean square error and fairly low r square score. So one would think this should be really there is a linear relationship somehow between the x1 and y, but in all fairness, the regression line is not really fitting the data that well, and we have a lot of residuals on both sides of the line. So that's our first candidate for a feature. Let's check the second one, which is feature number 2. Now this should actually be worse even than x1, but we'll give it a try anyway, and we'll see. Well, as expected, we have higher mean square error and a lower r square, and this is also attributed to heaps of residuals on both sides of the line. So clearly now we do not have a good fit that can predict y from feature 1 or from feature 2. So the very next step would be to explore why. Why is that happening? And to do that, let's plot the data and see how the data actually looks like. Now, when you plot this data, this is a 3D plot. And the only difference between a 3D plot and a normal plot is that when you add the subplots to the figure, you would just put the projection to 3D like this. The rest would be replacing scatter with scatter 3D, plot with plot 3D, and so on. And it will take two x's and a y, and then the rest is color and so on. But let's see what actually is happening with the data. Now, we know from the linear regression we did before that with feature 1 and feature 2, there wasn't really much of um, a regression power that can predict y from feature 1 or y from feature 2. And if we really maybe rotate this figure and let's see either feature of them, we will see that, okay, yes, this is typically what we have seen with the pair plot. This is kind of the same pattern that we have with the points, and the red line will actually go in the middle and you have a lot of residuals here. So this explains one part. Now if we check the other part, a bit of a spoiler here, this is also similar to what we have seen in the pair plot. Again, even if you pass a red line here in between, there will be a lot of residuals on both sides. The reason for that is that we are actually projecting, when we're doing the linear regression on one feature, we're projecting this onto this side or that side. And in both cases, we have a lot of residual. However, if you really look at the right angle, you would see there is a really good regression line there. The only problem is it needs feature 1 and feature 2. And if you remember, this is actually what we generated in the dataset at the top. Let's go back. So we said we need two informative features. These are the two informative features. So technically speaking, what we really need to do is just pass a line through these points and we should get a perfect regression. The only problem is that this is actually not enough because the points are actually scattered all the way. If you pass a line in the middle, you will have residuals on both sides of the line on this plane. The one thing that is actually correct here is that these data are actually mapped on a plane, and this plane is controlled by feature 1 and feature 2. So now we know what we're dealing with. We actually need to expand our regression model to include both features. So similar to what we've done before, the only difference that we do here is that the features we're selecting from X would be 1 and 2. Remember, the 3 is not included. And then the Y is the same. Everything after that is exactly the same. You will just fit the model, predict and get Y hat, calculate R square and MSE. When we run this, we will find an amazing MSE close to 0 and R square exactly 1. Of course, in reality, this actually doesn't happen, but this is because we are using here a synthetic data set. So how would that regression line actually look like? Actually, it does look like a plane rather than and not a line. And to plot that, we will need to generate all the points on this plane and then use the 3D plotter to actually plot this plane for us. So we'll make a 3D figure. This is just a normal figure. I'll just give it the name 3D to make it different from the others. And we'll make a 3D axis. This is the same thing with the figure add subplot 1 1 1. This means one row, one columns, and we'll select the first one in the first one in the axis list. and the projection here will be 3D because we are plotting a 3D. Now what we need is to just scatter the points. We'll put this x sub 0 and this x sub 1. These are the two features that we have, and then we'll plot y, and the color will be black. Now to map all the points on the plane that we are plotting, we need to get the minimum and maximum for each feature, because these are the two dimensions of this plane. And then we will generate a linearly spaced steps or values across the both features. We call it x range 0 and x range 1. And here we're saying we need 100 values between minimum x0 and maximum x0, and similar with minimum x1 and maximum x1. And we'll reshape both into 101, just mainly to make it a column, which we can then use when we pass into the predictor, the model that we have. Now comes the important part. These two on their own, they don't actually help us, because if you put them next to each other, you will have 0, 0, and then 1, 1, 2, 2, and so on. Let me illustrate. We'll go into this Python console on the side, and let's see np.linspace will take 0 to 1 and 3. We'll call this feature 0. Now if we check f0, we have these three values. Let's reshape them. And we have f0 like this. Now if we make f1 similar to that, we have both. Now we can concatenate both of them. We can use numpy.concatenate, and we'll give it f0 and f1. If you do that, it will concatenate both of them next to each other, on top of each other. This is not what we want. We want something like this: axis equals 1, and this will put them next to each other. But now you can start see the problem. We need the point 0, 0, 0 0.5, 0, 1, and then 0.50, 0.5, 0.5, and 0.5, and so on. We need a Cartesian product between both between values in both features. For this, we will use something called Meshgrid. It's a function in NumPy, and it takes the first linear space and the second linear space, and it will return to you two new arrays. Now if you see ff0, you will find it looks like 0, 0, 0, 0.5, 0.5, 0.5, 1, 1, 1. Now let's check f1. Sorry, f1. Similar thing here. We need to reshape these into one dimension. It will look like this. And if you do f1, it will look like this. Now if you put them together, so let me do f0 equals no. If you put them together, concatenate, we'll take ff0 dot reshape, or actually we can do it flatten even, and ff1 dot flatten, at axis 1. This this was not correct. I have to reshape them. Okay, so let's do that. So we'll reshape this by minus 1 1. The minus 1 in the reshape size means calculate the other dimension. So you specify one dimension and you calculate the other one. So we'll reshape this, we'll reshape that, and this would be the vectors that we have. Now this actually spans the entire space of both features because it has 0 and 0, 0.5 and 0, 1 and 0, and then 0, 0.5, 0.5, 0.5, 1.5, 0, 1, 0.5, 1, and 1, 1. So this is what we want. So to take it here in the code, we generated x range 0, x range 1, and then we used Meshgrid to generate x grid range 0, x grid range 1, and so on. And here we will define the points for our plane. So we'll call it plane x0, x1. These are the features we have, and this is just the name, so it can be anything really. And we will concatenate the same thing that we did here on this side. We'll just do the same here. We'll reshape these two minus 1 1 and reshape the other one minus 1 1 and then concatenate across the second axis. Remember, axes count from 0, so 1 here means the second axis. Now let's see what we have here. Technically you have a data like this, and this looks exactly as the number of samples, and on the other dimension would be number of features. Now these points are in the shape of the features that the model is expecting. The model was expecting any number of samples in rows and exactly 2 features on the columns. So now when we pass this into the predict, it will give us a new an array of predicted y's, or this is the y hat that we have. And now when we plot that, before plotting that, we need to reshape the points into the same shape that we have with the x grid range 0, because this will give you the mesh grid will give you the span of the surface that you are plotting on. So we're saying the z grid predicted equals z grid predicted dot reshape z x grid 0 dot shape. And finally, what we will need after that is just plotting x grid range, which is this column, x grid range 1, the other column, and the z grid predicted, which is this column. These are reshaped into a matrix which spans the entire surface of the plane. And we'll set color to red, RGB, and we'll put 0.5 for transparency, and so on. And let's run that. And there you go. This would be the plane that can fit this data. And if you can see here, if we really tilt it properly, it actually goes through the entire all the data that we have here, and not only that, it also covers or allows the data to lie on the plane, which is having the perfect angle there. And this actually justifies why we are getting an r square of 1 here, because this is the perfect fit. Alright, so there you have it. When you have when using a single feature doesn't really do the trick, we have to start examining multiple features, and with that we can we enter into higher dimensional regression. So you're having higher more features on the x-axis, and then you are doing a regression to predict a value on the y-axis. This can also expand to multivariate on the y-axis, so you'll be predicting two values. But usually, unless it is kind of a multitask training, so the two values do really need to follow the same pattern, or maybe they both actually are expected to go into a particular model. It's usually done with a single variable h. Alright, I'll see you in the next video to talk about classification.